This is Lesson 2, Dot Product, from the Grade 12 Calculus and Vectors course, from the 5th unit, Algebraic Vectors. In this lesson, we're going to be focusing in on the first of two products you can find between vectors. Between vectors, you can find something called a dot product or something called a cross product. We'll talk about cross product later in the unit. In this unit, we're just going to focus in on dot product. Now, it's important to understand that these two products give completely different results that mean different things. In fact, dot product only gives you a scalar, so it's called a scalar product, right? It just gives you a magnitude, no direction. Whereas in cross product, gives you a vector result. So we call that sometimes the vector product. So in this lesson, we're looking at dot product, sometimes called scalar product. In order to be able to calculate a dot product, we're all going to have to understand what a vector projection is. So that's the first thing we're going to look at in this lesson, is understanding what a vector projection is. And that's going to help us come up with this formula for dot product. Now, this is the formula for the dot product of geometric vectors. And then we'll also adapt that to come up with the formula for algebraic vectors. So before we get started on doing this lesson, make sure you head on over to jensenmath.ca. Once you're here, you can go to the Grade 12 Calculus and Vectors course. You can find the 5th unit. It's the second vectors unit, 5th unit in the course overall. And we are in the second lesson, dot product. You can get a blank copy of the lesson if you click Lesson Student. And then after we complete the lesson, you can try the practice problems by clicking on Worksheet. And after you try the practice problems, you can check your solutions by clicking on Worksheet Solutions and compare your results to mine. Also, I should mention it would be a good idea to watch this video as well. This one uses Mario Kart to give you a little explanation about an application of dot product. So let's get started. Okay, to start off the lesson, let's look at the definition of a dot product. And while I read you this definition, I'm going to reference this diagram so that you can get a good visualization of the components of a dot product. In this definition, we're talking about the dot product of two made-up vectors. We'll call them vector A and vector B, this red vector and this blue vector. And it's important to note when we're doing dot product, the vectors always have to be placed tail to tail. So vector A is here, vector B is here, so they're placed tail to tail. And we're doing dot product. This is the notation that would mean the dot product of vector A and vector B. Now, A dot B and B dot A, they would give you equivalent answers, so it doesn't really matter which one you do. They're both equivalent to each other. And they're both going to yield just a scalar result. They're going to yield just a number, just a magnitude. So the result is not a vector for dot product, it's just a magnitude. That's a key thing about dot product. That's why it's called a scalar product. It's just a magnitude. And to calculate the dot product, we need to do a product of two things, the first of which is very easy. The second of which is a little more complicated, where we have to involve projections. So the dot product of two vectors is the product of the magnitude of one of the vectors. So I've got vector A and B, so it's the product of the magnitude of one of those. I'll choose vector B. So the magnitude of vector B, that's the first part of my product, multiplied by, now the second part's the complicated part, it's multiply that by the product of the other vector, so vector A, that is applied in the same direction as vector B. So I need to multiply the magnitude of B by the magnitude of A that is going in the same direction as B. So this part here, magnitude of A that is applied in the same direction as B, that part right there is what makes dot product a little bit complex, but it gives it some great applications. And the notation for that, well, we have to talk about projections. To determine the magnitude of A that is going in the same direction as B, we have to consider the projection of vector A onto vector B. And this is the notation for that. This means the projection of A onto B. The subscript vector is the one that's getting projected onto. So I need to multiply, so if I want A dot B, I have to do the magnitude of B times the magnitude of the projection of vector A onto vector B. And how are we going to figure out the magnitude of the projection of vector A onto vector B? Well, if we look at this diagram, we can use some SOHCAHTOA to figure it out. But I guess I should backtrack and talk to you about what is the projection? What does that look like? There are three properties about a projection vector that I want to talk to you about. And notice this green vector here, this is the projection of vector A onto vector B. So what are the properties of this vector? How are we going to figure out what that vector looks like? Well, that vector has three properties. Property number one, if we're doing projection of A onto B, the projection of A onto B is always going to be parallel to B. That's property number 1. The projection of A onto B is parallel to B. So that means either in the same direction as B or the opposite direction as B. The second property is that the tail of the projection vector is at the same place as the tails of the other two vectors. So all the tails of all three of these vectors, the red one, the blue one, and this green projection vector, they're all in the same spot. The third property, since we know where the projection vector starts, we have to know, well, where does it finish? How do we know that the tip of the vector finishes right here? I know it finishes there because if I were to connect the tip of vector A, the vector that we're projecting, onto the tip of the projection vector, it has to form a 90-degree angle. That's what makes it a vector projection. That's why sometimes it's called an orthogonal projection, because of that 90-degree angle. So quick summary of the three properties. If we're projecting A onto B, that vector projection is going to be parallel to vector B. Its tail is going to be at the same place as the tails of the original two vectors. And its tip is going to be at a place where if I were to connect the tip of vector A to the tip of the projection vector, it would form a 90-degree angle with the projection vector. So those are the three properties that help us figure out the vector projection. Now let's come up with an expression for the magnitude of it by looking at this triangle right here. So looking at that triangle, notice that if we know the angle between the two vectors, and I should mention when we're doing dot product, like I said, we're going to have to know the angle between the two vectors when they're placed tail to tail. So if we know that angle, this would be adjacent to it, this would be hypotenuse. We could do a cosine ratio. Cosine of theta would equal the magnitude of whatever that projection of A onto B is, divided by the magnitude of A. And then we can just multiply both sides by the magnitude of A, and then we have the magnitude of the projection isolated. So I've got the magnitude of the projection of A onto B equals the magnitude of A times cos theta. So up in this formula for dot product, I can replace the magnitude of this projection of A onto B with the magnitude of A times cos theta. And there's my formula for the dot product. So this is the formula for A dot B or B dot A. It doesn't matter. It's the same result. And normally you'll see the A and the B written in reverse order. The order of multiplication doesn't matter. So often you'll see it written as the magnitude of A times magnitude of B cos theta. So that's the formula for dot product. And this is exactly what we just went over. The dot product is just a product of two things. It's the magnitude of one of the vectors times the magnitude of the other vector that goes in the direction of the first vector. And we figured out we can replace this with this. And then that gives us this new formula for the dot product. And this is the formula for the dot product if we have geometric vectors. Before we move on, let me just really make sure you understand what this projection vector is going to look like with a quick demonstration in GeoGebra. This program here is always showing the projection of U onto vector V. So with this projection, it's important to notice the three properties of this projection vector. If we're projecting U onto V, the projection vector will always be parallel to V. Its tail will be in the same place as vectors U and V, and its tip is going to be at a point where if it connects to vector U, that line would be perpendicular to the projection vector. So let me just move these vectors around and let's look at the projections. So notice the projection vectors, they're always parallel to V, the tail is always at the same place as vectors U and V, and it still always forms that 90-degree angle when connecting the tips. It forms that 90-degree angle with the projection vector. What happens if the projection vector moves over here? Well, notice if the angle between the vectors is bigger than 90 degrees, the projection vector is actually going in the opposite direction of vector V now. But it's still parallel to V. It's still parallel to V, and it still forms this 90-degree angle with the projection vector when we connect the tips, and the tail is still at the same place as vectors U and V. So it still has all the same properties, but just notice it's now going in the opposite direction of V. So a dot product, it can be negative. And that would indicate that it's going in the opposite direction of the vector that you're projecting onto. So now let's go back and do some examples. So this box is just a nice summary of what we've talked about so far. For two vectors, a and b, the dot product, a dot b, is equal to the magnitude of a times magnitude of b times cosine theta, where theta is the angle between a and b when the vectors are placed tail to tail. And theta is always going to be between 0 and 180. So we're always going to use this angle when they're placed tail to tail. We would never use that angle there. And the dot product is just a scalar. I've mentioned that before, but I can't stress enough that when you do dot product, you do not get a vector. You just get a magnitude, no directions. You just get a number, you just get a scalar. So dot product is often called a scalar product for that reason. So let's go ahead and try out this formula that we created with a few examples. And I should mention, this is the formula for the dot product of geometric vectors. There's a different formula for if we have algebraic vectors that we'll do later in the lesson. So let's try a few examples. Example 1, determine the dot product of each pair of vectors. So I've got two geometric vectors here. They're already placed tail to tail. I know the angle between them and the magnitude of both. That should be fairly simple and straightforward to come up with their dot product. Write either a dot b or b dot a, doesn't matter, they're equivalent. And that would equal the magnitude of a times the magnitude of b times cosine of the angle between them. So magnitude of a is 20, magnitude of b is 30, and the angle between them is 40 degrees. So we can evaluate that on the calculator, get an approximate answer. Just make sure your calculator is in degree mode. And if we evaluate that, we get about 459.6. Now, let me just give you a quick visual demonstration of what we found. And it wouldn't matter how you thought of this. We either found the magnitude of A times the magnitude of the projection of B onto A. We either found that, or we found the magnitude of B times the magnitude of the projection of A onto B. They're both equivalent. Let me just show you a visual representation of what both of those things would be. So if I were finding this, I would just be defining the product of that, the magnitude of that vector, vector A, times the magnitude of the projection of B onto A. And that would look something like this vector. Parallel to A, 90-degree angle there. If I were doing this one, that would be the magnitude of vector B, there's vector B, multiplied by the magnitude of the projection of A onto B. And what would that look like? It would look something like, I don't know, to right there, so that it forms a 90-degree angle there. So it wouldn't matter which of those two products I found, they would both give me the same result, 459.6. Part B. This one is a very special case of dot product that you're going to have to understand. If I want the dot product of m and n, so I'll do m dot n or n dot m, doesn't matter, would equal the magnitude of m times the magnitude of n times cosine of the angle between them, and the angle between them is 90. And cosine of 90 is actually 0. So it doesn't matter what these magnitudes are, 60 and 75, they're being multiplied by 0. So the dot product of two vectors when they're perpendicular to each other is 0. So that's going to be a really important property that's going to be very useful when working with vectors from now on. Geometrically, this product should make sense to you about why it's 0 as well if we understand vector projections. Right? If we're doing m dot n, really what we're doing is the magnitude of m, 60, times the magnitude of the projection of n onto m. And what does that projection look like? Well, if I'm projecting it onto vector m, it has to be parallel to m, and its tail needs to be right here, and its tip needs to go to a place so that when I connect the tips from n to the projection vector, it forms a 90-degree angle, and it already forms a 90-degree angle. So I can't extend that vector anywhere, because then it's no longer a 90-degree angle. So that vector, the projection vector, actually has a magnitude of 0. It's the 0 vector. So that's why the dot product of two vectors that are perpendicular to each other is always 0, because the magnitude of the projection vector is 0. Part C. This time the angle between the two vectors when they're placed tail to tail is bigger than 90 degrees. Let's see what that does to their dot product. So let's do v dot u. That would equal the magnitude of v times the magnitude of u times cosine of the angle between them. So that would be 85 times 100 times cosine of 120 degrees. So I know this time my answer is actually going to be negative. I know that for a couple reasons. First of all, I know cosine of an angle between 90 and 180. I know cosine is negative based on the cast rule. Only sine is positive in this quadrant, so I know this is going to be negative. The second way I know my answer is going to be negative is if I think about the projection vector of vector u onto vector v, it would look like this. It would be going in the opposite direction of v. That's the only way I could get the tips of these vectors to have a 90-degree angle with the projection vector. So here is the projection of u onto v. And notice it's going in the opposite direction of v, which indicates to me my dot product is going to be negative. And if I evaluate this, I get negative 4,250. So we went through 3 very specific examples for dot product of geometric vectors. The first one, the angle was between 0 and 90. We got a positive dot product. The second one, the angle was 90. We got a dot product of 0. And the third one, the angle was between 90 and 180, and we got a negative dot product. We'll come back and talk about this chart in just a second. I just want to fill this part out while it's fresh in our mind. So based on the angle, we can predict whether the dot product will be positive, negative, or 0. If the angle is less than 90, we get a positive dot product. If the angle is bigger than 90, we get a negative dot product. And if the angle is 90, the dot product is 0. So now that we're back at this table, give this table just a quick read. A couple things I want to highlight here. The most important parts of this table here are vectors are perpendicular if and only if their dot product is 0. I also want to talk about the commutative property, u dot v is equal to v dot u. We've talked about that a bunch. I'm not too worried about this bullet point right now. We'll talk more about that when we do applications of vector projections later. The associative property, this would be important to understand as well. It wouldn't if you were multiplying a scalar by a dot product, it wouldn't matter whether you multiplied that scalar by one of the individual vectors first and then did the dot product with the other, or if you did the dot product of the 2 vectors first and then multiplied that dot product by the scalar. It wouldn't matter. It would be equivalent. And lastly, for any 3 vectors u, v, and w, u dot v plus w is equal to, the distributive property works, u dot v plus u dot w. So there's just a few properties of dot product that you should know. Let's transition now to part 2, where we're going to now work with Cartesian vectors, also called algebraic vectors. So for given vectors in this form, the dot product is actually easy to find. So we have vector A and vector B. Vector A, we know its x and y components, and vector B, we know its x and y components. If we want to find the dot product of vector A and B, remember we're going to just get a scalar, we just get a number, just a magnitude, no direction. To calculate that scalar, we just multiply the x components of vector A and B plus the product of the y components. That's it. That's the formula for dot product of algebraic vectors. Really straightforward. So let's see how that works. Here's u and v. If I want the dot product of vector u and v, I just have to multiply the x components, 5 and 4, plus multiply the y components, negative 3 and 7. So I get 20 minus 21 equals negative 1. That's it. That's the dot product of u and v. Part B. I want the dot product of this vector u and this vector v. I could do u dot v or v dot u. Wouldn't matter. They're equivalent. But to find that dot product, just multiply the x components. So negative 2 and negative 1. And then add the product of the y components, 9 and 0. So this is the product of the x components. This is the product of the y components. Add them together. That's the dot product between the 2 vectors. So that's 2 plus 0. Dot product of u and v is 2. Part 3, mechanical work. So work is a great application of dot product. One of the applications of dot product is to calculate the mechanical work performed. Mechanical work is a product of 2 things: the magnitude of the displacement traveled by an object, and the magnitude of the force applied in the direction of motion. That's what makes this a dot product question. And the units are Newton meters, also known as joules. So I have an object moving, that's my displacement vector, and I applied some force to that object to get it to move that distance. So I'll call these 2 vectors, I'll call this my displacement vector, and I'll call this my force vector. So the work done to move the object that far would be equal to the product of the magnitude of the displacement, so the magnitude of vector d, times the magnitude of the force applied in the same direction as the displacement. So notice I translated the force vector so that it's tail to tail with the displacement so that I could figure out what magnitude of the force is in the direction of the displacement. So I would have to project the force vector onto the displacement vector. And what would that projection of the force vector onto the displacement look like? Tail would be here, and it would be parallel to the displacement vector, and it would stop at a point where that if I connected the tip of the projection vector to the tip of the force vector, it would form a 90-degree angle with the projection vector. So this green vector here is the projection of the force onto the displacement. So work is equal to the magnitude of the displacement times the magnitude of the force that is in the same direction as the displacement. We call that the projection of the force vector onto the displacement vector. Notice this is dot product. Work is equal to the magnitude of d times the magnitude of f times cosine of the angle between them when they're placed tail to tail. We talked about earlier in this lesson that if we knew this angle between them tail to tail, an equivalent expression for the magnitude of the projection of f onto d would be equal to the magnitude of f cosine theta. So you can see that work is actually just a dot product question. This is actually just d dot f, or f dot d, doesn't matter, displacement dot force. So it's a dot product question. Example 3, Max is pulling his golf cart up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. This hill is 100 meters long. Find the work that Max performs. So we established right here that when we're calculating work, really what we're doing is we're finding the dot product between the displacement and the force vector. So all I have to do is find the dot product between the displacement and the force vector in this diagram. All I'm trying to do, to calculate work, I'm trying to figure out the magnitude of the displacement vector, that vector, with the magnitude of the force vector that's going in the direction of the displacement vector. So times the magnitude of the projection of f onto d, which would look like that vector right there. And that's just the dot product between the two vectors. So I'm just finding, when I'm doing work, I'm just doing displacement dot force. And that just equals the magnitude of the displacement times the magnitude of the force times cosine of the angle between them when they're tail to tail. So in this question, it equals 100, that's the displacement, times the force, 120 newtons, times cosine of the angle between them, which is 20 degrees. And right, our displacement is in meters, and our force is in newtons, so our product is going to be in Newton meters, otherwise called joules. So we can evaluate this and get an approximate answer, and we would get 11,276.3 joules, or Newton meters. So that's it for our dot product lesson. We're going to continue with some applications of dot product in the next lesson, so make sure you stay tuned. Make sure you go to Jensen Math and get a copy of the practice questions now and give them a try, and use my solutions to check your work. And that's it.